thermodynamics, by definition, is looking at the energy changes that happen during a chemical reaction. The first law of thermodynamics I already talked about in the last video is it says that the energy of the universe is constant. Another name for it is the law of conservation of energy, which again says that you can't create or destroy energy. It simply just gets converted to a different form or transferred to another object. Internal energy, which is the capital letter E that you see. So anytime you see that capital E, we're talking about internal energy. And internal energy is the sum of the potential energy and the kinetic energy of all the particles in the system. And so the equation for internal energy is the delta E is equal to Q plus W. Q stands for heat, and W stands for work. Now, you may be thinking to yourself, well, she just said it was the sum of the kinetic and the potential energy, but now the equation brings in Q and W. Well, as you will see shortly, Q, heat, it's related to the change in temperature, which we talked about in the last video, and temperature is the measurement of how fast or slow molecules are moving, which essentially is directly proportional to kinetic energy. It's not the same thing, but they are proportional. And so that's where the heat comes from. And as you'll see on the next slide, I believe, work has to do with potential energy. And so that's where the Q and the W come in from. But to calculate internal energy, it's going to be the delta E is equal to Q plus W, heat plus work. Now, this part is very important. I would say that the calculations that you do in thermochemistry and in thermodynamics are not difficult. What's difficult is trying to figure out the sign, because mathematically the sign, whether it's positive or negative, is not always going to be, it's not always going to mathematically come out to be the correct sign. And so it's important for you to be able to know whether something's positive or negative based on the point of view that we're talking about. So remember, we always look at the point of view of the system, at least if you are looking in chemistry, which we are. And so when we're talking about Q, which is heat, if something is a positive Q, that means that energy is flowing into the system, or as we talked about in the last video, it's an endothermic process. If Q is negative, that means that energy is leaving the system, which is an exothermic process. So positive Q is going to be endothermic. Something has energy flowing into the system. And negative Q means that energy is leaving the system, or it's an exothermic process. The same sort of idea, conventions, apply to work. So if work is being done on the system, that means that energy is flowing into the system, the work is being done on the system, so you have a positive W. And then the opposite is true. If work is being done by the system, and so the system is exerting that energy, it's leaving the system, you have a negative W. And as you will see in the questions that we deal with in the problem set, it is very important to know whether something is positive or negative. And it's not always going to be clear it's going to be clear if you read the question, but it's not always going to say, work is equal to negative 752 kilojoules. You're going to have to figure it out based on what's happening in the question to the system. So this started, very important. Memorize that. Make sure that you can determine whether a number should be positive or negative. All right, so let's talk about work for a moment. Let's see. We talked about this equation in the last slide, and this one's new. So work is equal to negative P delta V. Negative P, the P is pressure, delta V is change in volume. This, for the purposes of chemistry and AP specifically, when we talk about work, we're usually going to be dealing with gases, and specifically gas compression and gas expansion. And so think about it in terms of this picture here on the right. So if you have a cylinder with some sort of piston that moves up and down, if gas is being compressed, and so we're moving this piston down, that means the work is being done on the system. The system is the gas, it's the particles. And whereas if you have gas expansion, and so this piston is moving up, that means those purple gas particles are doing work on the surroundings. And so that would be gas expansion. And so that's just an important sort of vocabulary thing to know about if a question references gas expansion or compression. Make sure you know what actually is being done, and so you know whether to make something positive or negative. A couple reminders when we're looking at work is that work and P delta V is going to always have opposite signs because, as I just mentioned, when gas expands, that means a positive W. That means that work flows out of the system, and then vice versa would also be true. The second thing that you need to remember when looking at specifically gas expansion and gas compression and this work equation is that when you have an ideal gas, work can only occur when the volume changes. And so if a gas is heated at a constant volume, then that means that the pressure is going to increase, but no work occurs because if you have this equation, negative P delta V, and it tells you that you are at a constant volume, that means this delta V equation is equal to 0, and we know 0 times anything is going to be 0. And so if you have no change in volume, so a constant volume, no work is being done. And then the last thing to remember is that the pressure in P delta V always refers to the external pressure, the pressure that causes the compression or causes or resists the expansion. It's not the pressure inside the container, it's going to be external pressure. And that will be clear to you in questions. Questions are not going to give you both the internal and the external, and you need to figure out which one to use. It'll be clear to you, but it's just important to know that when we're looking at this equation, work is equal to negative P delta V, it is going to be the external pressure that we're going to want. So these two equations are ones that you are going to need to use and know for this particular unit. All right, and this, I'm not going to go through and read this. You can read through it at your own time, but remember that we will be using enthalpy. We talked about this in Chem 1. So enthalpy, which is delta H, is going to be referring to the heat associated with the chemical reaction. And specifically, as it says here, we're going to be looking at when you have a constant pressure. And so the basic overall of this equation or of this slide is showing you how these various equations are derived. But it's important to know when we're talking about enthalpy is that the delta H, the change in enthalpy, is equal to the heat associated with the chemical reaction when you are at constant pressure. And so if you are at some sort of system that's not a constant pressure, we cannot assume that the delta H is equal to Q. And because delta H is equal to Q when we're at constant pressure, the same rule applies for the negatives and the positives. And so remember that if you had a negative Q, that was exothermic. The same applies if you're looking at delta H. And so if you have an exothermic reaction, it's going to be a negative delta H. If something was a positive Q, we said that was heat is being absorbed by the system. That's an endothermic process. And because we're saying that Q and delta H are the same at a constant pressure, that if you have a positive delta H, that's the same. And the other thing I do want to mention here, just to remind you, is that sometimes you will see a thermochemical equation in which the delta H is written in the chemical equation, and it will be written on either the reactant side or the product side, and that will be an indication of whether something is endo or exothermic. And so if it's exothermic, it's going to be written as a product. And if something is an endothermic reaction, it'll be written as a reactant. And hopefully you remember that from Chem 1, but that's just a reminder. The last thing I'm going to do in this video is go through a couple of calculation questions just to refresh your memory on how to apply the stuff that we just talked about. And you will for sure have more practice problems looking at work and things like that, the previous equations in the problem set. All right, so consider the following reaction and accompanying enthalpy change. So we're looking at the combustion of propane. Here's the balanced equation. Here's the delta H for the equation. So is this reaction endothermic or exothermic? Well, first of all, it's a combustion reaction, so that should be your first clue. But if you can't remember that, you'll look at the delta H. The delta H for this particular reaction is negative, and if something has a negative delta H, that means it is, oops, let me go back. That means it is exothermic. And how do you know? Well, you know because of the negative delta H. Would the reactants or products have a lower amount of energy? The products would, because it's an exothermic reaction. We talked about that in the last video. Question 3. If you burned a sample of propane and produced 1 mole of carbon dioxide, what would be the amount of heat released or absorbed? Well, first of all, it's going to be released because we're talking about an exothermic reaction. But in order to figure out just how much heat, you got to look at the balanced equation. And so according to this balanced equation, if you produce 2,200 kilojoules of energy, that's going to be produced when you have 3 moles of carbon dioxide. But in this case, it's asking us about 1. And so you can set up a stoichiometry question, a stoichiometry process in order to figure this out. So we have 1 mole of carbon dioxide. Moles is on the top. We're going to put 1 on the bottom times the coefficient. And from the top equation, coefficient is 3. And we are trying to find X kilojoules, and we'll put the delta H on the bottom. So 2202.0. And if I do my cross multiplication math, you get 734 kilojoules of energy are released. Now, I did not include the negative sign because it specifically asked you for the amount of heat. It can't release or absorb a negative amount. And so I knew that it had to be the absolute value, and then I was going to tack on that word absorbed or released at the end to answer the question. So that's why I ignored the negative sign. All right, final question. A propane camp stove has a tank that is almost empty, has 5 grams of propane in it. Would it have enough propane to boil water for a cup of coffee, which is about 500 milliliters, and assume that all the heat can be transferred to the cup? So this introduces the next thing that I'm going to be talking about in our next video, but it introduces calorimetry and looking at Q equals MCAT. And so that's the equation that we're going to use. And remember, Q equals MCAT looks at the amount of energy required to do something. And so the first thing I'm going to do is take the 5 grams of propane and figure out how much energy is released when that 5 grams of propane is burned. All right, so after doing a basic stoichiometry question, stoichiometry process like we did in the last question, so if you burned all 5 grams of that propane in the stove tank, you would release about 250 kilojoules of energy. And so the second part of this question is to figure out how much energy it takes in order to, or is required to boil that 500 milliliters of water. And so if we're trying to figure out how much energy is required to do something, that's when we're going to use the Q equals MCAT equation. Okay, so as a reminder, Q is the amount of energy required to do something, M is mass, C stands for specific heat capacity, and delta T is the change in temperature. So because we're dealing with water, and water has a density of 1 gram per milliliter, if you have 500 milliliters of water, we can say that there are 500 grams. The specific heat capacity of water, as I'll talk about in the next video, is 4.184. That's a constant that you should know and memorize. And then my delta T, so the change in temperature. The final temperature, which is boiling water, and then the initial temperature, it didn't give it to us in the question, but I just used about room temperature, which is 21 degrees. Obviously, in a real scenario, if I wasn't writing the question quickly, it would have to tell you the temperature, but I just assumed it to be 21 because I didn't give it to you when I wrote the question quickly. But if we do this math, you end up with 162 kilojoules of energy is required. And so if we compare these two answers, well, the answer to the question is yes, you have enough energy, because when the water is boiled, 250 kilojoules of energy are going to be released, and only 162 of it is needed to boil that water. So the answer to the question is yes, there is enough energy to boil that water. There's enough propane to boil the cup of water.